好，我这边先讲讲话，看会 delay 多久。好，看起来大概有15秒的 delay。我刚刚动了一下，其实15秒后才看到自己动。好，对，那也是谢谢同学，我们现在还在下课时间啊，那个一会儿就开始今天的这个 session。听得到我讲话的话，可以 say hello。哎呀，有听得到我讲话吗？Can you hear me? Good. Okay, so we'll start on time when when the clock of my computer hits 3:30. Okay, so oh yeah, welcome back to DSP, and this is our third time meeting over here from on YouTube, and the streaming session. Today we are going to talk about homework number 5 and number 6. Actually, one person asked a question from any previous homework. You could, if you have a question, you can please feel free to raise it. And we do have a question, actually an interesting one, from homework number 4. And so let me just go through the kind of go over, and of course you can still anytime. I have asked the TAs to collect your questions in the meantime. Okay, so you can either type something over this chat, which occurs on the right of my browser, and also I think the TA created a Slido, sort of a Slido session that runs in parallel. So if you prefer, you can communicate to TA instead of raising your question over here to everybody here. Okay, if you want to raise a question, that is to say, if you want to ask anonymously, you can please contact the TA through their Slido private session. Okay, but otherwise we're good to go. So today I collected the TA sent me this list of questions. The first question, so let me just go over this first. And the first question on this list is, I will just read it. Why we should use low-pass filter to convert discrete signal to continuous? Is there any other way to reconstruct the signal? Okay, so I think this is a good question. So let me try to review the scenario. Let's say we have a discrete signal right? Always we just draw a few tabs equally spaced in time. So n from 0, 1, 2, 3, 4. And so I think let's just still review the concept that when we want to convert it back to continuous, we first of all see all the samples as spikes, and then we just low pass filter it, okay, as that is mentioned. So an ideal low pass filter, actually in this course we haven't really touched about how in any real world filters frequency response is never perfect, but conceptually at least we want to have this. We want for every spike in the time domain here, we will place a scaled copy of the sync function, and the sync function has a property that is 1 somewhere, and it crosses 0 exactly at integer multiples of the sampling period. So that's of course you can scale. You can also stretch the sync function in time, but here we stretch it so that exactly the 0 crossing will be aligned with the integer multiples of the sampling period. So we just place them all together, and you see the net deflect would be an interpolation, right? So if you just add all the sync together, you see interpolation. Okay. So the question is why? So equivalently, so if you challenge us, why do we absolutely always need to construct the signal using a low pass filter? Can we use something else? So of course you can. Okay. So my answer would be yes. Because let me put it this way. So when we have discrete samples, and we know that it must be originated from an analog continuous time signal, okay? But from analog to digital, let me put it this way. From analog to digital, this conversion is many to one, right? And that's exactly the issue of aliasing, right? So usually aliasing is not preferred. It's really not preferred, right? So that is itself is an assumption, you know. If for some reason you prefer aliasing, okay, if for some reason you assume that all the analog signal in the world is actually at a high carrier frequency band, so by sampling it insufficiently, we'll move it to the baseband, right? So if that's the scenario, sort of a communication scenario, then when you reconstruct the signal, you just shift it back to where it belongs originally, okay? But usually, unless otherwise mentioned, when we reconstruct the signal, we assume that the sampling is free from aliasing, male aliasing, free of aliasing. Okay, so if under that assumption, then when we reconstruct the signal, we apply a low pass filter. That is to say, we convolve these spikes in time with the sync function, whose 0 crossings exactly occurs as the integer multiple of our sampling period. And in the end, we have a smooth low-pass filter version of the collection of these spikes. Okay, hope that's all I want to say about this question so far. I hope it is clear. But feel free to try to require me to further clarify what I said. Typing in your comment from the chatting, the chat box on your right. Okay. So the next question, the question number 2 is regarding zero padding. So I'll read it in Chinese first. The question is, zero padding 真的有增加资讯量吗？真的有增加资讯量吗？如果有的话，为什么不无限 zero padding? Okay, I think this is an interesting, very, very good question again. So to translate that into English, the question is, does zero padding increase the amount of information? Does it increase the amount of information? If so, the natural thing to do might be, wouldn't it be great to just infinitely pad as many zeros as you want to further increase the information. Okay, so that doesn't sound right. And if you have that in mind, I agree with you. My answer is zero padding does not increase information. Okay, because all you add is zeros, and zeros that do not add any information. But I wonder who asked this question. Okay, because I don't recall covering this topic in this course, but instead we cover this topic in my other course, my audio signal processing course. So I wonder what's the context under which you have this question in your mind. Okay, zero padding. Usually, that's what we do when we use, for example, fast Fourier transform to accelerate convolution in time. Okay, so you have an FIR filter, which we're going to talk about how to design. If you have an FIR filter you design and you want to use it for processing a signal in the Fourier domain, you can do that. But zero padding is a step you need to consider in order to avoid certain artifacts. So I wonder what's the context this person had in mind. But my short answer, zero padding means that you have a block of signal and which has a shorter length, and in order to calculate this Fourier transform we add zeros, and that absolutely does not increase information. Okay, and the only purpose I can think, the most common purpose for the reason you do that is because you want to perform filtering in the frequency domain. Okay, and you do that in order to avoid what is called cyclic aliasing. So please type in, if you are online, please share with the rest of us why you have this question in mind. And my short answer is zero padding does not increase information. But another scenario it might be helpful is for, again, we do not cover this in this course, unfortunately. Let's say if you are have a scenario of, this is really out of scope of our current schedule, but I want to share with you. Another reason for padding zeros is for spectral estimation. So let's say you have a signal and you are pretty sure that there is a tone, 一个单音一个 tone. There is a tone of certain frequency in the signal. And your task, if your task is to figure out the frequency of that signal, you pass zeros to the signal first, and you compute the Fourier transform to find the peak. And by adding zero, even though you do not increase information, what you gain is resolution. You see more points in the frequency domain. So let me actually draw a picture. Okay, let's say if you have a signal of such length, and you're sure that it has some sort of a sinusoid in it. Okay, so let me draw it quickly. Let's say if you have a signal like this, a certain length, and it looks like there is a sinusoid. And now the question is, what is the frequency of this signal? Okay, and so to do that, some of you might have learned or heard that you can just take this block and perform sort of a discrete Fourier transform. Not discrete time Fourier transform, but discrete Fourier transform. That is, and the fast version is FFT. Okay, so you just send this through FFT, then you see if this is really a sinusoid, you should see a peak somewhere. You should have a spike in the frequency domain. Let me just briefly denote that the frequency domain as F. Okay, so you should expect to see a spike, a peak somewhere, and there's also, this is actually a digital sync function. Okay, so you expect to see a peak somewhere, right? But the benefit, let me just briefly say it because this is really out of scope of this course. If you just simply add zeros before doing FFT, just increasing the length of the block, but by adding zeros. Okay, by adding zeros, what you gain is because the length of FFT is going to be exactly the same as the length of your signal in time, the block in time. So if this signal has an FFT, if the number of samples is, let's say, 512, then in the frequency domain you are also going to see 512 discrete points in the Fourier domain. Okay, so that increases your resolution. The resolution has been increased. You do not gain information, but you gain resolution. Okay, so yeah, this is itself a rich topic. I'm glad that somebody is curious. But please, if you are online if you are the original person that asked the question, please pose kind of 心路历程. Why do we have this question? I'm curious. Okay. Right. So with that, I'd like to go into the third question I have on my list. So this third question really is great. I love this question. Okay. So I'll read it in Chinese first. So the question is, let me maybe present it closer to the camera. The question is, 以 t 为取样周期对连续时间系统的脉冲响应啊，取样得到了离散时间系统脉冲响应，那就有一个公式在这边。那这个公式 so let me translate that. So this is to say we are sampling an impulse response, a continuous time system's impulse response, which is denoted by h sub c of t. If we just sample it with a period of t, capital T, and to obtain a discrete time impulse response denoted as h of n. So in the textbook, actually, in the textbook we have a formula h of n. H of n is equal to this t times the continuous time impulse response sampled at integer multiple of t. Okay, and the question then is, why do we need an additional factor t in front of hc of t? So why do we need to multiply this factor in here? So, and it seems that actually, I thank you for raising this question. There is indeed a discrepancy. Okay, what's written on the textbook is indeed with a factor t here, but on Professor Oppenheim's video, he did not have the factor t over there. Okay, so there's a discrepancy. 有点不一样啊. Thank you for raising this question. So my answer is, the short answer is about the unit of your output. Okay, so of course we can kind of wave our hand and say this is not going to be a big deal. Right, it's just a scaling factor, and the result is also it's only going to be multiplied by be or be not multiplied by this factor. So there's only a matter of scaling. So it's not super important. But let me try to answer your question by saying that at least the short I have a longer answer. Okay, the short answer is that we want to make the unit correct. The unit 单位 So let's say starting from what do I mean the unit? What do I mean the unit? So let's say we have a signal hc of t, and we are going to convolve it with an impulse response, which is hc of t. In the continuous time domain, we call the result y continuous of t. All right. So if I ask you, let's say for example, if x has a unit of volt, right? Potential, electrical potential, right? Voltage. Okay, if x is the voltage and h has no unit, h is just 1, 2, 3, 4, 5. It's a scalar. It doesn't have any unit. Okay, then my question is: Have you ever thought about what's the unit of y of t? What's the unit of y of t? Or even better, let's say x is the current. Okay, x is amp. Okay, if x is amp and h does not have a unit, then what is the unit of y? What is the unit of y? It turns out that if you try to figure that out, okay, so the definition of convolution is an integral, right? It's an integral of h. You just basically treat now the integrand is tau, okay, and we are going to multiply x with a flipped around copy of h. So that's a definition of convolution, right? Okay. So now, to answer that question, the question regarding a unit, if this does not have any unit, and this is current times something integrated over time, the result is what? Is a charge. A charge, let's say, accumulated somewhere on a capacitor. Okay, so this unit is going to be Coulomb. So this is a charge, and in this example, we convolve a current with a unitless impulse response. Then after taking the integral, the resulting function is a function of time, and that function, that output, the the output variable has a unit of charge, which is different current time multiplied by time. Okay, and that's why we need to multiply by time here. So that's kind of my short answer to satisfy your goal. So it really depends on your goal. If your goal is to design a digital filter, then this T is not super important. But meanwhile, in contrast, if your goal is to simulate an analog system, let me say that again. Let's say if your goal is to simulate an aircraft or a vehicle or a pendulum or a circuit, okay? If your goal is to simulate an analog circuit in discrete time, numerically, people in HW5, I bet they know how to take care of this scaling factor, okay? So that's why you need to make sure the unit is correct. So that's a kind of a short answer to address the reason why we need a scaling factor which is has a unit of time, unit of second, okay? But then to further extend the question, I have a longer answer. So let's still start from this equation, okay? Starting from this equation, if all we want to do is to approximately calculate continuous time convolution, okay? So note that this is an integral, right? An integral. What is an integration? Integration is a limit, right? Integration is a limit. A limit of what? A limit of if we just let this small incremental time difference, we call this t, and let t approaches, let's say t approaches 0, okay? And then we are going to realize integration is really a limit of summation, okay? In what sense? So let me put this, so this is the function and integrating over tau, okay? So all we need to do is to put in x of tau, replacing tau by integer multiples of t. So let's say that the dummy index is m. So m tau, so tau is replaced by m times t, okay? And similarly, hc of also t is actually, t does not affect the integration, okay? So let's leave t for here for now. And then tau, again, tau is m times t, right? So we know that by definition, integral can be expressed in terms of a Riemann sum, okay? 黎曼河啊 Riemann summation, okay? 这是一个黎曼河。黎曼河看起来像一个女孩子的名字，黎曼河。Alright, so yeah, so that's the first step, okay? So integration is really a limit of summation. We all learned that, okay? That's basic calculus. And next, so let's say, so if t is small enough, so that is to say, if t is small enough, how small is small enough? That's kind of that's for you to determine. But if t, let's say roughly, if t is small enough, then we can say this summation, we can say the limit, with a finitely small enough t, we can say that we can just ignore the limit, and let's say now t is small enough. Yes, so with a finitely small but non-zero t, small enough t, we can say that y on one hand, on the very far end, on one side of the chain of equations, we have the output. The output at any time t is going to be approximately, okay? This is not an exact identity, but it's going to be approximately just this expression. We just rewrite this expression. Okay? Alright. So let's say now, let me use the space over here. So now, define. Let's define a y of n. Okay, now let's discretize this output signal. Okay, let's discretize this output signal by defining it as the continuous time signal sampled at n times capital T. That small number we were talking about. Okay, we can do that. Then I want you to check that. Then in this setup, this setup, you can show that okay, all we need to do. Let me just go on a few steps further. Okay, so we are going to substitute this time t with n times capital T. Okay, is it actually clearer now? Yeah, I'm afraid that the lighting is too strong. Okay, anyway. Oh, let me adjust my lighting. Okay, to be a little weaker. The lighting is too strong. Yeah. All right, this should be better. Okay. So I was gonna say that by discretizing our output signal, we are going to substitute this time t with n times capital T, which is our small period, sampling period, actually. And you'll find that then that is to say in the far end right here, we are t is here, right? We are also going to replace this t by capital n times capital T. Okay, so now let's say this t is equal to n times capital T. Okay, so in the end we say we have, and then yeah, n, we have a summation, and this should be roughly equal to, yeah, approximation. This is an approximation, and HC MT. And this, what is this? This is x of n, right? Times HC. Oh, I'm sorry, I missed the t here. Okay, yeah. Let me, yeah, it's bad streaming in here. I forgot about this term. Okay, so you see, even I made a mistake. So this detail, due to the presence of this detail here, we do have a factor of t. Okay, yeah. Let me rephrase. To compute, to replace, to approximate, to calculate an integral by a Riemann sum, you do need to have kind of this t in front. Okay. Let me come back to this. Yeah, let me come back to this later. But I was gonna share with you that then we have a factor t here. I'm gonna share with you that here this now we are substituting the time t with n times n times our sampling period. Then here we have hc of n times t minus n times t. And what is this? This is equal to hc of basically, no, h, not c. H of, no, this is what it is. Okay, this is what it is, and with a t in here. Okay, right? So let me put another piece of paper. So you see what I'm going to say? I'm going to show you that in this framework, indeed, we ever want to approximate. If you ever want to approximate this, running out of my desk space. If you ever want to approximate this continuous time system, then we have y of n is approximately and y of n is simply yc, the original output signal sampled at nt. Okay, so and the result really is approximately h of n convolved with something, and that thing over here is t times h of t times what? Let's say we are convolving with let us just denote what we convolve here by h of n. Okay, And you will see that just by comparing the coefficients here, by comparing everything here, you'll see that this h of n really then is totally equal to t times hc of n times t. Okay, so that is to say this t comes from Riemann sum. This t comes from Riemann sum. Okay, and so that is say when we design, or I like to say it's a simulation. Okay, when we simulate an analog system in discrete time, and an analog linear time invariant system has an impulse response, and you sample it, but please remember to scale your analog impulse response by this factor t, and this factor t comes from the Riemann sum. So I want to share before I leave this topic, I want to share with you the picture really is when we are. So what is integration? Integration in general, integration is to calculate the area under curve, right? Integration to calculate the area under curve. Okay, and so to calculate area under curve, we all know that by definition we can approximate the area by the sum of these rectangular stripes, right? We all learned that in fundamental calculus. That's the idea. That's the idea. That's the idea. And since this is time domain, we say that now in our previous notation, the distance between the distance of these rectangular stripes, 这些长条啊, the width of the stripe is our big T here. Okay, and so that factor of T really comes from here. Okay, and so we are going to, when we calculate the area under curve, and approximately, please remember that it's not merely a summation, but still, it is a summation, but you need to scale the summation by that factor of T. And that's really how this factor comes, where this factor comes from. Okay, I'd like to pause a bit. Before I move on. Let me check. Okay, so I'm not looking at my YouTube studio, so let me check if you have any comments here. Okay, so somebody calls 11平, 11平. Okay, thank you for sharing your sharing some comments here. And Gao Zhengyu 的话, yeah, sure, you can ask the next question of homework 5. Maybe it will have to be in the end of this streaming session. Okay. Okay. So I hope that addresses the question why there's a factor of T. Okay. Short answer is you need to make the unit correct. Longer answer is really the spirit of integration. Convolution is integration in continuous time. And to simulate this operation in discrete time, you need to calculate, what you need to calculate instead is a Riemann sum. Okay, the Riemann sum, and there the factor of T occurs over there. Oh, then let me move on to the fourth question. Okay, the fourth question. The fourth question, actually, I think two different people asked a very similar question. Okay, the fourth question is, I'll read it first. Why we need to the lighting? Okay. Anyway, why we need to calculate the phase response in continuous time of the causal system to prove its slope is always negative. Okay, and so, yep, I'll change the other side. So the question is in homework number 4, and this is homework 4, the F part, by the way. Homework 4, the F part. Okay, the F part. In the F part, remember that we had a continuous time. Actually, in that homework, I also invited you to work on bilinear transform, which is also the topic of this the homework 6. Okay, And so in that homework, what did we do? We were studying the all-pass filter. Okay? We were studying the all-pass filter, and I argued that by mapping it from discrete time from the z domain to the h domain. So let's recall the scenario. The scenario is that we had an all-pass filter, which has what? I hope everybody remember that an all-pass filter has what? Has 1 0 and 1 pole. 1 pole inside. Or they can have many zeros and many poles, and they all occur at reciprocal locations. Okay, so let's say we have 1 pole inside the unit circle, which is r away from the origin, and then you need to place a 0 outside, which is exactly at the same frequency, same angle, but 1 over r away from the origin. Okay, and this is z domain we're talking about. Z domain. Okay, so in homework number 4, we were saying that we want to convince ourselves that the group delay of an all-pass system is always negative. Okay, so of course you can. There are many ways to argue that, but then in homework number 4, I invite you to first use bilinear transform. And by now, I hope it is clear that bilinear transform, what it does is to map the unit circle. It maps the unit circle. Okay, the unit circle, let's say from minus pi to 0 to plus pi. So it maps the unit circle of z domain to the imaginary axis in the S domain. And this is S domain. Okay, and also just because of conformal mapping, what begins on the left of your path. Now we are going counterclockwise. 逆时钟, 不是顺时钟, unfortunately. We're going counterclockwise around the unit circle, and what remains on the left, what's on the left of your path, the contour remains on the left after an analytic mapping. Okay, so a conformal mapping. So the inside is mapped to the left-hand side of the S-plane. Okay, and so with some calculation, we also worked on the fact that if we have a pole zero pair in the Z domain at reciprocal locations, then in the S domain you have a pole on left half plane and a 0 on the right half plane. And in our previous streaming session, if you haven't viewed the video, I believe we have recorded that. So we talked about also we talk about that the phase response is exactly which angle. The phase response really is this angle. Okay, it is this angle. That's what I remember. Okay. So then the question now, this question occurs again. The person, your fellow student is asking, why do we bother to show that the slope, the slope of the phase response is negative? Okay. And by now, I hope that you know that the implication. Okay. The implication of a phase response slope being negative is that its group delay is always positive. Okay, and what the question might be, the next question might be, why is this a big deal? Why is this a big deal? Group delay being positive, isn't it always the case? Actually, another of you raised a very good question. Since he has a strong point to make here. The next question is, a causal system's group delay is positive for all frequencies, right? Causal, right? Output cannot occur before the input comes in. Causality, right? So if that's the property, then group delay is a delay. So everything has to be delayed. That's the meaning of the causal system, right? And so why do we bother to verify that indeed the group delay is always always positive for this all-pass system? Wouldn't it be always the case for any causal system, true or false? True or false? Okay. And these two questions are related. I take this there. This is an important question. Okay, true or false. What do you think? I'd like to pause a bit, maybe 1 minute. Can we kind of, can those of you that are online, true or false? Does a causal system always have positive group delay for any frequency? I'd like to pause a bit. Causal system in Chinese, OK， 一个 causal 的 system，causal stable 或者说也 stable，OK，causal stable system 它的 group delay 永远都是正的吗？有没有答案？如果都是正的话 ，if it's always positive, why do we bother to verify? Okay, indeed, for an all-pass filter, the group delay is always positive. Okay, so I'm waiting for you to type in something. Okay, we come back to that. Okay, in the meanwhile, let the TA, please TA, if our TAs, if the TA is around, please upload the problem and solution. 好，yeah。我先去到中文好了。那个今天有一些技术问题 ，we have some technical difficulties. So some of you reported that the kind of the video is not clear today. Yeah, it's not clear today. Yeah, so we rely on 其实这是 camera 的自己 auto focusing 啊。它如果 auto focusing 有问题的话，我实在也没有办法啊，因为那这个可能会跟今天房间的这个亮度这些都有关的啊。我想先暂停一下，我想请 TA create 一个 vote 啊，就是说我刚刚问那个问题，group delay 是对一个 causal system group delay 是不是永远是正的啊？是不是永远是正的啊？如果是的话，为什么会 bother 还要去问说 all pass filter 它的 group delay 还要去做这么长的推导啊？那如果不是的话，就有可能是表示有可能是负的，那这是什么意思？这中间有没有一个矛盾在这边 ？Causal system means causality means the output cannot occur before the input comes in, right? But why on earth would be a frequency experience a negative group delay? And what does that mean? What's an example? Okay, 所以我一边等你们 TA 回应啊 ，TA 在的话 ，TA 能 say hello to 大家吗 ？TA 有在吗？TA 有在吗？有在的话，请 create 一个 online 的一个 vote 啊。那我来看一下，奇怪，这个为什么会不清楚啊？为什么今天的 video 会不清楚？Before we move on, I think I need to play with the video a bit to see if, yeah, wow, somehow this is interesting. I might need to. Okay, so 我发现有一个问题是会闪光啊，这非常有趣 aliasing. This is an example of aliasing. When I turn on my lamp. When I turn on my lamp, there's the flashing effect. Now I see the problem, at least one of the problem. 它会闪它会有这个横向的条纹出现，that is bad. Okay, I'm gonna stop talking for a while before before while the TA is setting up the Slido survey. So actually, I'd like to take a 5 minute break before coming back. Okay, so let's say the 5 minute break. 好，那个 so I'm back. So the TA is yes. Please go to Slido event code 30192. Okay. Alright, so think for I'm not going to check that I invent, so I'll let the TA report. Okay. But the answer, as some of you already typed in here, the answer is no. Okay, the answer is that a causal system can have a negative group delay for certain frequencies. It is possible. It's entirely possible. But then the next question is, how do we resolve the kind of contradiction? Okay, there seems to be a contradiction. Causal system output cannot occur before the input comes in, but how would any frequency experience a negative group delay? So I want to kind of share my my thoughts with you on this important topic. So idea is that group delay, okay, the meaning of group delay really, let me switch back to my other viewer. So the meaning of group delay is really when we have a signal in time. When we have a signal in time, and group delay is meaningful only when we talk about a narrow band signal. Okay, and that is I believe that is part of our. This is homework number 5. Yeah, we will deal with this idea, right? So group delay is only meaningful when we talk about a narrowband signal, a kind of a carrier frequency being amplitude modulated by a slower varying envelope. Okay, so let's say this is a wave packet. This is a wave packet, and which has a center frequency. If I just enlarge this packet, which has a center frequency of a roughly constant frequency, right? And then it goes through a system. Let's say if the system somehow is able to, this is about prediction and cancellation, okay? And we know that we can, it's possible to, let's say, subtract the next sample from the previous sample, something like that, okay? So it is possible. It's entirely possible to design. Or let me put it this way: it's entirely possible to design a system. Let's say this the carrier frequency omega 0. The carrier frequency is omega 0. Okay, and the signal is expressed as some kind of envelope signal, times cosine of omega n, where omega 0 denotes a carrier frequency. Okay, and now if your filter has a 0, okay, now we are in the Z domain. And if your filter has a 0 at this angle, exactly at the angle omega 0, okay, and the 0 could be somewhere, let's say the unit, further assume that the 0 is very close to the unit circle. There's the 0 over there. Okay, there's a 0 over there. That means that when the signal has this frequency, the magnitude at that exactly that frequency at the output side, the magnitude is going to be attenuated significantly. It's going to be the magnitude is going to be small. Okay, the magnitude is going to be small, and this is still a causal system. So what's happening is that the output could be, okay, so at this moment is coming in the signal, but then it realizes that the system is trying to cancel it. That's the idea. If it realizes that the system is trying to cancel it, then the output can look like that. Okay, it's being cancelled after a few moments. okay, it's cancelled. It's largely cancelled. Okay. All right. So does this system violate causality? No, because still we have no input before, we have no output before the input comes in. Okay. So it doesn't violate causality. But in the meanwhile, if you look at the center of mass, so the output, the envelope of the output, that peak of the envelope actually occurs before the peak of the input envelope of the input. Okay, so that's why now the group delay is going to become negative. In the meanwhile, causality is not violated. Okay, so there's actually no contradiction, and this is a good question. I want to share with you. I hope this is getting clearer. Okay, so I'm hoping that the video now with this lighting, I decided still I need strong lighting. Okay, so I hope that the video will remain clear, acceptably clear till the end. So with that, we will come to the kind of main topic today. Today we need to talk about homework number 6. Okay, homework number 6. Okay, homework number 6. What it is to I want you to explicitly find out a discrete time IR filter, which is characterized by a difference equation. Okay, a filter is always characterized by a difference equation. So now the topic of last week's video was about designing, borrowing the idea from analog filters. But let's say we have an analog filter with good performance. Can we sort of change it into a discrete time filter, okay, a digital filter? And there are two main methods that we are comparing. One is the previous one. We can sample the impulse response, which is called the impulse invariance method. And the second method is this homework. Okay, the second method is that we want to perform bilinear transformation. And by bilinear transformation, a good property is that what is a stable system remains a stable system, and there's no aliasing. Okay, so that's all in the video as well as in the textbook. So the idea is that we start with the example of a Butterworth filter. Okay, so we have what is called a Butterworth filter. A Butterworth filter is in the continuous time, in the continuous Fourier domain. And so in the design process, I hope you understand this, that we do have a circle. But please know that this circle I'm drawing is in the S domain, not in the Z domain yet. Okay, this is in the S domain. And in the Butterworth filter, we have this property. Okay, I'm going to need my 我要需要我的小抄哦，稍微看一下。So in the Butterworth filter, we have this analog response that HA of S must be equal to 1 divided by 1 plus S divided by J omega C. Okay, omega C is the color frequency in the continuous time domain, and up to the nth power. Okay, so in this case, in the video, am I running out of my screen? I hoping yeah, probably not. Okay, good. Okay, so to the 12th power. To the 12th power. Okay, so it's been figured out that this will satisfy the design specification with also in the video, the Professor Rosenheim talks about that he shows that let me explicitly write this down. The color frequency in the continuous time domain of something like 0.76622, that will work. If you just convert this filter to a discrete time filter, it will satisfy the specification in the discrete time domain. Okay, so the idea is that this is in terms equal to HA of S multiplied by HA of minus S. Okay, and the reason is that when we change to a negative frequency, we negate, we add a negative sign here, the complex transfer function is conjugated. Okay, that's a symmetry of Fourier transform, and so that's why when we multiply the two of them, the result is simply magnitude squared. Okay, and so we know that now, for better or for worse, this expression has many poles around a circle, and that circle has exactly the radius of omega c. Okay, and so exactly it will the magnitude squared will have 12 poles, 12 poles, and they are equally spaced around the circle. 它是等角度啊。So we will have 6 on the left hand side and 6 on the right hand side, and they are all equally spaced, which means that they are all 30 degrees apart. 30度，各都相隔30度，30 degrees apart. Okay, so let me draw a quick figure. And this system is going to have exactly 12 poles located at, this is 15, 45, 75, and they are all separated by 30 degrees apart. Exactly 12 of them. Exactly 12 of them. And we basically assign the 6 on the left to our transfer function, and the other 6 would belong to, they are the pole of actually HA of Guahu minus S. Okay, right. So anyway, so that means that an expression, we can have an expression. Now we can have an expression for the analog transfer function. So we can have an expression for the analog transfer function, and it will be HA of S is going to be basically S minus S0, S minus S1, and there's going to be 6 poles, which are located as, this is S0, S1, S2, S3, S4, and S5. These are the 6 poles, okay, in the analog domain. And here, the top part here, we will need to move that omega c to the top. Okay, this omega c will be converted to the top, and is raising its power to the 6th power. Okay, so that's our analog transfer function. So in this homework, we figured that the bilinear transform we have is S of z. S of z equal to 2 times 1 minus S z inverse divided by 1 plus z inverse. Okay, so that means if we just define our h of z, as we substitute S of z into the analog transfer function, and that's simply a definition, then this is going to be a mess, I promise. Because we have a product of 6 factors. But wait, you might be able to simplify the picture a bit by noting that these poles all occur in conjugate pairs, right? So S0 is going to pair with S5, and S1 with S4, and S2 with S3. Okay, so let's before we plug in, before we make this substitution, I'm pretty sure that we still have omega c to the 6th power over here. That's still going to be there. So let's pair S. So the top part. So let me put it here. Okay, so let's just say that S, we can assume S minus S0 times S minus S5 can be re-expressed as something, can be put together. They can be grouped together. Okay, they need to be grouped together, and as something S squared plus as plus b. Okay, you can do that. And similarly, for pairing s1 with s4, let's just keep saying s squared plus cs plus d. And s plus minus s2. I personally find this a bit easy to work through manually to derive the answer. S squared plus es plus f. Okay, so 6 coefficients. I'm pretty sure you can figure that out. These are all because those poles are located. The poles are located at known locations with a known radius. Okay, so in principle you can figure these A, B, C, D, and E, F. Okay, I bet you can do that. So here now let's put in S squared plus AS plus B, and S squared plus CS plus D, and S squared plus ES plus F. You need to figure out the detail. Okay, I'll leave that to you. And then now S, what is S? S is a function of Z. Okay, S is a function of Z. So now what you need to do is to just just faithfully put in 2 times 1 plus Z inverse, that to divide 1 minus Z inverse to the square. Okay, and plus A times exactly the same thing. Okay, 1 minus Z inverse, 1 plus Z inverse. Okay, and plus B. So that's one part, as well as the second part. Okay, there is again you see I forgot about the factor of 2. Okay, and similarly 2 times that square plus C times no, actually this is 2 squared. Okay, so you see there are a lot of places you might make mistakes here and there, but please be careful. 2 times that plus D, and so on and so forth. The bottom part, our denominator has 3 factors. Okay, 3 factors, and on top still we have omega c to the 6th power. Okay, and the next thing, so that's the idea. So actually part of the question I was asking, you still remember, I was asking how many poles and zeros do we have in H of Z. So how many poles? And the answer is indeed the 6th order filter. It should have, no surprise, indeed it has 6 poles. It has 6 poles. But interestingly, if we just further clear things up, to make things do some bookkeeping. Okay, 稍微整理一下, do some tidy, rearrange the factors. So now it seems that we have 1 plus Z inverse and to the 2nd power, which occurs over here. So the idea is that let's what do? We should multiply the top part and the bottom part, both of them, by 1 plus, let's try to multiply. Okay, let's multiply the 2 of them. Let's move this factor of 1 plus Z inverse square. Let's move it to the top from bottom to top. Okay, and similar here, 1 plus Z inverse to the 2nd power. Let's also multiply that and raise it to the numerator. And similar here, 2 times 1 plus Z inverse something, okay, square. Let's also move this. So in total, we're going to multiply the numerator and denominator, both of them, by 1 plus 6 Z inverse to the 6th power, such that for the denominator at the bottom, we do have a polynomial of Z inverse, and that is important. Okay, I want you to be aware of this step. Okay, so the answer is that indeed, then after so the next thing you do is to, hopefully you can find that we have B 1 plus Z inverse square plus A times 2 plus Y minus Z inverse 1 plus Z inverse. I'm just going to show one of them to you. 4 times 1 minus Z inverse to the square, and yeah, coefficients. That's one part of it, and we have two other factors to all multiply together with factors such as C and D and E and F occurring in their places. Okay, so at the bottom, indeed, when we multiply all three of them, we do have a polynomial of Z inverse, and on top we have exactly omega C cutoff frequency to the 6th power times 1 plus Z inverse also to the 6th power. So the answer is yes. We have how many poles and zeros do we have? The answer is we have 6 poles and 6 zeros. Okay, and so that's part B. That's part B. That is for part B. Okay, this is homework 6, question 4, part B. Okay, so by the way, the TA will announce the solution. Okay, so he managed to figure out all the coefficients somehow. We thank him for doing thank them for doing that. So that's part B. 6 poles and 6 zeros. Okay, and my next exercise. So now let's continue to part C. Okay, so the part C, I want you to write down the corresponding difference equation. Okay, so the corresponding difference equation. By the way, the correct answer for the part C should be a difference equation with a 6th order difference equation. Okay, so but before I move on to write down that 6th order difference equation, note that the denominator has 3 factors, and each of them is a quadratic form, is a quadratic function of Z inverse. Okay, so in chapter 6, later in this semester, we will talk about structures. We'll talk about structures for computation. Okay, so to implement an IR filter, well, you can write down the 6th order equation, which is a mess, because you can expect that what we are going to do is we need to multiply, we need to expand. We need to find out what exactly is that 6th order polynomial, which is a pain. Okay, 非常的琐碎的一件事情. It's doable, but it is a pain. But in chapter 6, we can talk about why don't we. It is also possible to really to develop a kind of a cascade structure. A 6th order system can be decomposed, can be expressed as the product of 3 2nd order systems. Okay, and 2nd order systems is easier to. We don't actually to implement this filter. We don't absolutely need to figure out explicitly the linear coefficients for the difference equation. Okay, so but we will leave that for chapter 6 later in the semester, near the end of the semester. But let me just continue for the sake of completeness. I will just show you. I'll just show you briefly in principle. Okay, for part C, now we have for part B we do have an expression like this. Okay, when we have an expression like this is our h of z. Okay, this is our h of z. This is our h of z, and so in part C, all you need to do is to express h of z as omega c to the 6th power, and on top we know that 1 minus z inverse to the 6th power is what? 1 plus 6 z inverse. I'm just memorizing. 16是吧？16、15、20是吧？Something like that. 20 z to the minus 3rd power, and it's going to be a symmetric polynomial. Okay, so that's on top, right? That's on top. And at the bottom, you need to figure out. So I'll just roughly express. And at the bottom, it should be clear that we do have a 6th order. We do have a 6th order polynomial. And let me just roughly say it's going to be ak z to the minus k, where k is from 0 to 6. Okay, 7 coefficients, and which gives you a 6th order polynomial of z inverse. Okay, And then with that, we know this is just simply b of z divided by a of z, right? So we can, then the corresponding difference equation is going to be a0 y of n. We all know that I write a few terms. Y n minus 1 plus and plus a6 y of n minus 6 equals to b0 x of n plus b1 x of n minus 1, the previous sample, all the way to b6 x of n minus 6. Where are these AB coefficients? A coefficients are occurred in here, and B coefficient simply is 1, 6, 15, 20, and 15, 6, and 1 times omega c to the 6th power. Okay, so it's pretty tedious, I agree, but you can, I'm sure most of you are good enough to automate this by a, now you know how to exactly all the details, you might be able to write a program to automate this process, this design process. Okay, so the reason I want this to be in this homework, that because I sort of feel that the video itself talks about the general principle, design principle. Yes, you can do bilinear transformation, and the frequency response is going to be monotonically decreasing, which is a good thing for this Butterworth filter. But then how do you implement this Butterworth filter? You need to go through this tedious process. So that's why I want to include this as our homework problem. Okay, I'd like to pause a bit right now, because I think I have addressed all the questions so far, all the questions, this except the additional question that Gao Zhengru is going to ask. Okay, so let me continue. So actually in part D, I think another person wants to make sure what is meant by part D. Okay, in part D of this problem, I was asking that suppose we have a floating point processor. We have a processor, then I will ask you how many floating point multiplications are required for every sample of output. Okay, and the answer is pretty straightforward actually. I meant starting from the result of part C, and we can rewrite this as y of n. For every sample, every new sample, you want to compute a new sample of output. This sample of output can be expressed as what? As you move a0, 1 over a0 to the right hand side, and everything here is going to be a1 y of a minus 1 with a minus sign, okay, and so on, all minus sign, and plus b0 x0 xn to b6 xn minus 6. Okay, and so of course we can pre-compute coefficients such as minus a1 divided by a0, minus a2 divided by a0, and minus a6 divided by a0. You can pre-compute these coefficients. I'm sorry, I'm running out of space. Okay, you can pre-compute these coefficients, as well as a0 divide b0, b1 divided by a0, and b6 divided by a0. Okay, you can pre-compute these coefficients and store it somewhere. And these are the coefficients you need to use in order to calculate every output sample. Okay, you just figure out the past output samples and feed them back to your equation, and also the input sample, the current sample, as well as 6 previous samples, and you multiply them respectively with these pre-computed coefficients. So in the end, how many multiplications are there for you to spend? So you need to calculate 7 multiplications here and 6 multiplications over here. So the total 6 plus 7 is 13. Okay, that means that for this IR filter, for every output sample, it takes 13 maybe floating point multiplication to complete. That's the computation load. For now you have a low pass filter, a beautiful low pass filter, I should say, a low pass filter with monotonically decreasing frequency response, which is awesome, absolutely good. Okay, yeah. So let me also mention that I like to take this chance to mention that in the coming weeks, 2 weeks, okay, we talk about FIR filters, okay? So FIR filters are easier to design, but in general, they have a larger computation load. Okay, to design a low-pass filter, it might take up to more than 60, maybe 100 multiplications. Whereas here, it only takes 13 multiplications, and this is pretty small. Okay, this is very much affordable. 很容易可以做得到的啊，所以anyway, so we will just proceed slowly because this past week is really only the first week we talk about filter design. And filter design is really the most important topic for our semester. So I want to make sure that we are on the right track and enjoying working on different problems. Okay. So let me check the chatting box. Let me check the chatting box. Okay. Okay, so the TA says most of you answered no, and that's correct. Okay, the answer is no. And so Gao Zhengyu, so but for those of you who answer yes, there's nothing. Yeah, please don't feel bad about it. Okay, so this is a question that has been in many people's mind. Okay, so I want to take this chance to openly share with you that this is a concept. Okay, so Gao Zhengyu said. 1 over z inverse should not be contained in the minimum phase filter. Okay, homework 5. Okay, 5至18B 啊，5至18B. I'd like to take another maybe 2 minutes break. Okay, let me check what is there in homework 5 and I'll get back to you. Okay. But let me also say that if you don't have any further question to ask, you may feel free to dismiss now. I'm going to address additional questions. Okay, so I'm back. I just took a look of that homework in homework number 5. Okay, let me check my screen. Oh, it's entirely blurry. Come on. Why are you entirely blurry? Okay, good. Oh, so strange. Okay, so I'm going to talk about homework 5. There's a question of it's actually an exercise on the lighting. The lighting. Shoot. 不太清楚啊，不太清楚，太强了。好，发我们习惯这样子的大小才行。哎 ，OK， 5字一定要放横的啊。好，那5至18B 了。所以它这边是一个 ，OK， we have a transfer function, a system function of z inverse 1 plus 1/3 z inverse 1 plus 3z inverse and 1 minus 1/2 z inverse. Okay, so we know that let's draw a diagram to see where the poles and zeros are located. So we do have it seems that we have a pole some here, and the pole is minus 1/3. Okay, we have a pole right here, and we have 2 zeros up there. We will address this factor because the question really arises how we how do we deal with this z inverse when we need to find a minimum phase system that has exactly the same magnitude response, right? The question is to find the minimum phase system that has exactly the same magnitude response. And so here that's one pole, and where do we have 2 zeros? We have a 0 inside and 0 outside, it appears to me. Okay, so we have 0 here at 1/2, and we have a 0 somewhere in -3. Okay, -3. Okay, all right. So to have so it turns out actually this is cool. Yeah, immediately I note. I haven't worked on this myself, but immediately we know that this is these two things here are going to be the all-pass part, right? Just by chance. This is just by chance. Okay, just by chance that this is the all-pass part, right? That is the all-pass part. So we say now let's say this is an all-pass filter times a minimum phase filter, right? The two of them multiplied together. So the all-pass part, so immediately just by inspection. Let me say by inspection, okay? By inspection, the all-pass part is already there. We don't even need to compensate placing a virtual location, something like that. So all-pass part just by inspection is this part. And I hope I'm correct right here, okay? So that's the all-pass part. Okay, and the remaining part is pretty interesting. Now I have to say it is pretty interesting. Okay, the remaining part. So if all pass is that, so the remaining part I argue H mean, but then Gao Zhongyu said the TA said it's not correct. But the remaining part. But let me just follow your thought. The remaining part is the minimum phase part is this. 1 minus. So here we do have what? We have no, this is gone either. This is also gone. Okay, so the remaining part is on top. We have a 0 inside in this circle, and at the bottom, what we have? We have nothing. So this is maybe we should say this is. So this is getting back to the old issue. That old issue. How do we deal with the invert itself? Do we count that this is a pole at 0 or a 0 at infinity, right? And is this a 0 at 0 or a pole at infinity? So this is really I hate this topic. I really hate this topic. Let me think. Let me think. Do we include this in the minimum phase part or not? Okay, if we include it here, is there any trouble? Is there any trouble? And we say this is a causal system, right? A causal system. So anyway, this let me continue. Okay, let me continue by saying that this is Z inverse, right? Times 1 minus that. Okay, 1 minus that. But first thing, I think you also notice that this factor, whether it belongs to the minimum phase part or the all pass part, does not affect the magnitude, right? Because Z inverse of 1 over Z inverse when Z is e to the j omega. That's a frequency response. Okay, this frequency response is gonna be what? Is e to the j omega. It is e to the j omega, and it does not affect the magnitude response. Yeah, this factor does not affect the magnitude response. So I could say, so the question really becomes that if we leave it here, can we still call it a minimum phase filter? That's a question. Because now currently I'm leaving the factor inside in here, okay? But if when I do that, we can make sure that this is satisfied. I mean, this thing I call, maybe I shouldn't call it H mean. I call it H residual, okay? I leave this factor here, then the magnitude response is going to be the same as H2 of Z. Okay, at least that is satisfied. Okay, this is satisfied for sure. So, but when we leave it here, this, what is this? This is Z, right? This is Z. This is Z, because 1 over Z inverse is Z. Okay, 1 over Z inverse is Z. Right. So do we call it a 0? Do we call it a 0 at the origin, or do we call it a pole at infinity? So this is tricky. You know what? If you include this in the term, then if you take this as a 0 at 0, then here we do have, then we satisfy the criterion that all the zeros are inside the unit circles, right? And there's no pole. So in that regard, this thing can be called a minimum phase filter, right? But if you think of this as a pole at infinity, then infinity is not inside the unit circle. Then by including this, leaving it in here, this expression does not have all the poles and zeros inside the unit circle. Okay, so if I grade your homework, I'm gonna give you full credit. Yeah, 我觉得这个可以满分，我觉得这个无所谓，因为 I can't argue, because what's tricky is that in this homework, it does not say if the system is, whether or not the system is causal. And I think that's a problem. That is indeed a problem. That's indeed a problem. Okay, so if you think 1 over Z inverse is Z itself, what is Z? Z is one sample advance. So then this system is not causal. And so given that it's not specifying whether or not the system is causal, I'm going to say or stable, right? It doesn't say anything. it has, to have a Fourier transform, the system needs to be stable. Okay, but it turns out that here what we encounter here might be now a non-causal system. Okay, a non-causal system. I think it is fine to leave it here. Yeah, I think it is fine to leave here. And my answer is indeed, h mean of z. So if I have to answer, I would say h mean of z is this, okay, which has a 0 at 112 and another 0 at the origin. Yeah, I think this is correct. It is correct to leave it here. That's my opinion. Let me check the chat box again. So people are thank you all for still sticking here. So there is a long conversation between Zhengyu and TA, so we will leave them to figure out. 你寄了一封信啊。好。0 at the origin. And 对啊 yn 减1等于 xn yn 减1等于 xn means that what? This is time advance. I'm looking at TA's comment. Not a causal system. Thank you. Yeah, so we agree. That's good. So let me kind of still I can agree with the TA that by noting that this is a non-causal system. And so maybe what is important really is not the definition of whether or not this system is minimum phase, but how do we implement the system. I mean, in practice, it's not that important to call it a minimum phase filter or not a minimum phase filter, right? What is more important is how to implement it. So as long as we all agree that this is going to be a non-causal system, and we have been aware of this, I think we're fine. Yeah. Whether or not to include that 1 over the inverse, to leave it in the minimum phase part, or to throw it to the all-pass part. If we throw it to the all-pass part, that it is totally fine, because as I said, it's not going to affect the magnitude response, whether or not you place it. Because if you go around a unit circle, e to the j omega is always 1. The magnitude of e to the j omega is always 1. So it's not going to affect the magnitude either or not. Either you put it in the all pass or in the minimum phase. Yeah, so both are fine. 好，那我想我在这边再多待个几分钟。那if you do not have further questions, you can feel free to dismiss. And thank you very much for joining me here today. And so next time, I hope that sooner or later we can get back to the classroom. Yeah, I'm not sure. Yeah, because in 2 weeks we schedule a classroom session. Yeah, still it is on the schedule. So I hope that we can get to see each other. Maybe half of you, because the university still suggests that at this point, the university still suggests that for any class larger than 40 people, we need to stay online. Okay. But anyway， 谢谢大家。好，那其实可以下课了。我会再多待一点，因为这边有时间差，大概有20秒的时间差。谢谢。